and welcome to this video on, this is for OCR or the Salters course. This is for atomic structure. My name is Chris Harris and I'm from AlleryTutors.com, and yeah, the whole point of this video is for revision purposes. So we're basically just going to go through an overview of the atomic structure section of the Elements for Life topic in the Salters course. Now the slides that I'm using here, they are available to purchase. They're great value for money. If you just click on the link in the description box, you'll be able to get a hold of them there. But they are great for your revision, enhancing your revision, other revision techniques you've got. You can put them on your tablet, your smartphone, etc. It's just a different way, and I suppose that because each bit comes in little bits, it's maybe a little bit more manageable to use, but they're there if you want them. So, like I say, this is dedicated to OCR Salters, and it matches these specification points taken from the syllabus. So if you're doing the Salters course, this should be perfect for you. Okay, so we're going to start with the atom. Now the atom is actually obviously very small, and we have an incredibly small nucleus. Okay, it's really small. You're probably talking about relative size. Some people have akin this to, if you put a garden pea in the centre of Wembley, that is probably about the size of the nucleus of an atom compared to the perimeter of the stadium. Now that's just, you know, what we've heard from some sources. So some people may correct me on that, but that it basically gives you the idea of the scale of this thing. But the nucleus is very small, contains protons and neutrons anyway in the middle. Electrons are in the shells, and they orbit the nucleus, and they take up most of the space of the atom. Now you need to know the relative charges and masses of these. So for proton, the relative charge is +1. The mass of it is 1. Neutrons have no charge, neutral, so that's 0 charge. Relative mass is the same as that of a proton. And electrons have a negative charge, that's -1, but their relative mass is 1/2000. So it's not 0, and they do have a mass, it's just very small. Remember, this is the relative mass as well, not the actual mass. Okay, so in the periodic table, obviously we have the mass number. This is the top number. This tells us the number of protons and neutrons in the nucleus, which is this top number here. The atomic number, or also known as the proton number, just tells us the number of protons in the nucleus. And remember, in atoms as well, all atoms are neutral, so the number of protons equals the number of electrons in atoms. Obviously, if it's an ion, then that's going to change a little bit, so that's an important note to make. Okay, so we're going to look at the history of the atom and how it's developed, because it hasn't just arrived, we haven't just known about it, it's actually been added to and amended over the time period. So you can see here that we start in 1803 with John Dalton, and he basically came up with this idea. He said that all atoms are spheres, and he said that each element was a different sphere. Very simple idea, but it was a start, okay? And that was contributed by John Dalton way back in 1803. A good while after that, actually, after John Dalton came up with that, J.J. Thomson decided to have a go, and he actually discovered the electron. He added to that model, and he said the atom wasn't solid and was actually made up of other particles, and he came up with the plum pudding model. Basically, he said that most of the atom was positive, and you had negative electrons that floated around inside it, and he called the positive bit the pudding bit, and the negative electrons were like the plums in it. Obviously, back then, they used this model to try and explain it to people, and they must have eaten a lot of plum pudding back then. Yeah, that's basically why it's called that. And very shortly afterwards, we had Ernest Rutherford, who came along just over 10 years later, and he discovered the nucleus. So, and he said that the nucleus was incredibly small, it was positively charged, and he also concluded the atom was mainly empty space as well. But he said it was made up of this negative cloud of electrons, so it was like a fuzziness around the atom. Now, he did an experiment to prove this. Well, his students did actually. Him and his students, which were Geiger and Marsden, they basically took a lot of credit for this experiment. But he did the gold leaf experiment, and what he did is he fired alpha particles at a thin bit of gold leaf. Most of them went through the gold leaf, and that basically allowed him to conclude that most of these were empty space. A small number were deflected back. Now, remember, an alpha particle is positively charged. They were deflected back because they hit something that was had the same charge. It was positively charged. So if they were deflected straight back, it means they've hit the nucleus, which very few of them did. But some were deflected because obviously they came close to the nucleus, but not exactly to it. So that concluded that the nucleus was actually positive, and the nucleus is incredibly small because most of them went through. 1913, so again, very, very shortly after, so they're coming thick and fast now. Niels Bohr had a go at it and actually said, well, Rutherford couldn't actually be right. He said especially about the cloud bit, he said the cloud would actually collapse into the positive nucleus because obviously they're oppositely charged. And what he proposed was, he said there were actual shells. We had fixed energy shells, and these energy shells had a defined amount of energy. And he did an experiment to prove it, just like Ernest Rutherford did. So basically he fired electromagnetic radiation, and it was absorbed by the atom. The electrons in particular absorbed some of this, and the electrons obviously moved from a lower energy shell to a higher one. And when they move back down to the lower energy shell after they've emitted it, they give out some radiation or emit radiation. And that was proof for Niels Bohr that actually there was shells and you had defined levels. So you couldn't have this cloud theory. So basically this is kind of what we see today. Now, obviously we can adapt to that, and we've added extra bits onto there as well, because we know we don't just have shells, we now have these subshells, and we call this the quantum model. Okay, this is the model that we have today, and basically this allows us to explain ionization trends, which you'll see later on in the course. But we had p and d orbitals, etc., and you'll see them later on in this video, and that was evidence for obviously we've got subshells in our atom. Okay, we need to look at something called nuclear fusion because we're looking at the atom, so we need to look at what things we can do with the atom. So elements are being formed through fusion reactions, okay? Really common in the sun, okay? The sun has got loads of fusion reactions happening all together. When you fuse things together, it means you're bringing them together, you're forcing them together. So fusion, like I say, is the forcing together of two nuclei in particular, okay? And these make a heavier nuclei, and if we've got a heavier nuclei, it means we have a new element. So this type of reaction, understandably, obviously it needs to be done at very, very high temperatures and pressures. You have strong repulsive forces between two nuclei. Remember, they're both positively charged. So trying to push these things together is going to be remarkably difficult to do. And obviously, due to the extreme conditions that we need, these reactions are very common in the sun because the sun does have these extreme conditions. And obviously, we form helium from two isotopes of hydrogen. Just be prepared to write an equation down to show nuclear fusion. You can see here that we've got, obviously there's hydrogen and there's another hydrogen isotope. We fuse them together. All we do is just add the top and bottom numbers together, so it's pretty straightforward. But this number here is unique to the element, so whatever the proton number is will be unique to that element. So that's how we know this is helium, because helium is the only element with a proton number of 2. So look at the proton number and that will tell you what the element is. Okay, so make sure they all balance. Obviously, that's pretty important. Okay, larger stars, these are like really, really big stars. These can fuse nuclei to form heavier elements than helium. Okay, so these are stars which are bigger than the sun even. These are huge stars. So, for example, oxygen and silicon can be fused together. And, well, we can fuse other atoms together to form oxygen and silicon, but they can fuse together as well. These obviously have higher temperatures and pressures to allow this to happen because you're now trying to fuse really positively charged nuclei together. So you're going to need really extreme conditions to do that. And obviously, large stars eventually, what they do is they explode at their end of their life. We call this a supernova, which is a massive explosion of a large star, of a giant star, should we say. And what it does, it sends all these bits of elements and fragments right across the universe. Some of these fragments are huge, and some of them have actually been formed to form some of the elements that we have on the Earth today. So actually, we are a product of a star that exploded a long, long time ago. So yeah, that's basically where these elements come from. So thanks to these suns and these stars, that are fusing these elements together, then we have the materials and metals and elements that we do today. Okay, so we're going to look at electron configuration. Now, these electron shells are split up into 4 subshells. We have the S subshell, which has 1 orbital. This can hold 2 electrons. We have the P subshell, it has 3 orbitals and can hold 6 electrons in total. The D orbital has 5. The D subshell, has 5 orbitals and that can hold 10 electrons. Remember, each orbital can hold 2 electrons each, so that's where we're getting the 10 from. And the F orbital has, the F subshell, sorry, has 7 orbitals and can hold 14 electrons. Again, each orbital can hold 2 electrons. So you'd see like an example here. So if we look at shell number 1, the subshells in shell 1 is just 1s, and that can hold 2 electrons. In shell number 2, we now have a p orbital within shell 2, so it's 2s and 2p. So in total, shell 2 can hold 8 electrons, and shell 3 can hold up to 18 electrons. You've got 3s, 3p, and 3d, and you can see here that we form 18 electrons in total. So yeah, as long as you know obviously how they're structured, it gives you an idea of the number of electrons in each shell. Okay, these are also known, you might know these, see these numbers as well. Instead of shell number, you might hear them called principal quantum numbers. So just be aware that they could be using that term in the exam as well. It's just the same as shell number. Okay, basically the higher the shell number, the further away from the nucleus it is. So shell number 3 is further away than shell 1. These have much higher energy than their other ones because they are a lot further away from the nucleus. So as long as you can relate the distance from the nucleus in terms of the shell number and energy, that's the main thing. So the further away you are from that nucleus in terms of the shell number, then the more energy it has as well. Okay, so let's look at some orbital shapes. Okay, remember we looked at the 4 different orbitals that we looked at, or the 4 different subshells that we looked at, and then we looked at the orbitals within that subshell. So now we're going to look at, obviously, we're going to look at the s orbital, and we're going to see what it looks like and how many electrons we can fit in. Now you can see obviously we fit 2 electrons in there, but it's a spherical in shape. It's a sphere, holds 2 electrons, and basically the electrons can move anywhere within that sphere, anywhere within there. Okay, that's what it basically means. Now the p orbital is a little bit more complicated. We have 3 orbitals, each one can hold 2 electrons, so we've got 2 times 3, so that's 6 electrons in total. So they give them really kind of boring names, unfortunately. They call it a px orbital, which looks like a figure of 8, as you can see. And that's the one that's lying on its side horizontally. The py orbital is vertical, and the pz orbital is coming out towards you. It's like a 3D shape. Now, all these orbitals are 90 degrees to each other, as you'll see there. So they all kind of cluster together. Obviously, you've got all 3 close together like that, and this forms the p subshell. We take all these 3 orbitals, the px, py, and pz orbital, that forms the p subshell. Now, there are 3 p orbitals, like I say, they're in the shape of dumbbells, or the figure of 8, as you can see on there. They can hold 2 electrons, and basically that electron can move anywhere within that coloured bit of the shell. So anywhere within the blue bit, the electron can be. Okay, that's where the electron can move to. You might also, and you're going to hear this maybe a little bit later on as well in the course, where you hear about spin pairing. Basically, it's where we've got 2 electrons that are occupying 1 orbital. As long as they spin in the opposite directions, that's the lowest energy conformation. So you might have 2 electrons in this orbital here. One will spin one way, one will just spin the opposite way. So we just call that spin pairing. As long as you've got an awareness of that, that's the main thing. You'll see diagrams with arrows going up and down. That's to show the spin, which way they're moving. Okay, so you'll see them on these diagrams. This is the diagrams I was talking about. So let's look at electron configuration. Okay, so we need to know the different parts. The big number in the front tells you the shell number. The letter tells you the subshell that it belongs to. And the little number there on the top tells you the number of electrons in that subshell. So this is 1s2, for example. So let's have a look at the electron configuration for iron. Now, what we need to do is look at the, because this is an element we're looking for, this is the number of protons, but the number of protons equals the number of electrons. So iron will have 26 electrons in total. So it has 1s2, 2s2, and you can see here, just with the arrows, they're going up and down. So that's showing the different spin. That's what I was talking about before. 2p6, 3s2, 3p6, 4s2, 3d6. So basically, if you add up all of them, they should add up to give 26. But this is the electron configuration of the elements. And this is just showing the energy diagram, showing how the electrons fill. So 1s is the lowest energy. Remember, this is the one that's closest to the nucleus. As we go further away from the nucleus, like the 3d, it's higher in energy. Okay, and this is just showing how the electrons fill. and the box represents an orbital, whereas one of the levels here represents a subshell, and obviously the number in front tells you the actual shell number. Okay, so we always fill from the lowest energy upwards, as you've just seen before, so that's quite important. And we fill the orbitals singly first, then we pair them up. So you notice here we've got them all singly paired. We're not pairing these ones up. They'll always occupy single orbitals first. This is because of electron repulsion. They repel each other. I liken this a little bit to like a bus. I certainly find this where I live anyway, where you get on a bus and everybody sits on their own seat first. If there's a spare seat, they sit in it. Some people even put their bags next to them because they obviously don't want anybody sitting next to them. But it's funny because people behave like that as well. They sit on their own seat, and then only if they have to, when another person gets on the bus and all the seats are full, then you have to sit next to another person on the bus. So it's a little bit like electrons. They prefer to sit singly first, and only if they have to will they actually sit next to another electron. But yeah. It seems to be very similar. That's what I find anyway. You might think different. Okay, so it's kind of the same reason. Okay, but don't write about buses in the exam, obviously. Okay, so we're going to look at electric configuration of ions. Now with ions, all we do is you just add or move electrons from or remove electrons from the highest energy level first. Okay, we always remove from the highest level first. So the electric configuration for calcium, or Ca2+, basically this loses 2 electrons. And these two come from the 4s orbital. So you can see here, this is the electric configuration for calcium. We lose the 4s2, and now we just have basically this configuration here. So this is the configuration for calcium 2+. Now obviously you need to check your numbers as well. Calcium is given the electric configuration, has the proton number of 20. So it has 20 electrons to start off with. We lose 2 electrons. Because it's Ca2+, so now we're left with 18. So make sure all these little numbers add up to 18. So we lose, on the diagram here, we lose the 4s, there it goes, and what we're left with is that configuration there. So they might get you to fill in one of these energy level diagrams as well. Okay, so as for the configuration, we can use noble gas symbols as well, a shorthand method. As you can see, some of their methods are quite long, but you've got to be careful. Read the exam question really carefully and see what they'll accept. Always best erring on the side of caution unless they allow you to do so. So let's have a look at potassium. Potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, so this is the electrical configuration for potassium. Now you can see here, this bit, the first bit, has the same electron configuration as argon. So what we could do as a shorter version is we can just put AR in a square bracket instead. So for example, we can write it like that, and that's just the shorthand version, and this is using the noble gas symbol to symbolize that. So this is basically telling us the noble gas configuration of argon plus that is the same as that. But please read the question carefully because they might not get a mark if you just write that. They might want the full configuration. Okay, transition metals, they're a little bit different, these. Okay, so they behave differently. So we've got the electric configuration for Fe3+. What they do is they lose 3 electrons, okay, to form obviously Fe3+, 2 from the 4s and 1 from the 3d, okay, which is a little bit strange. So, well, let's have a look. Here's the configuration here, as you can see. And what we're going to do is we're going to remove the 4s orbital first, or the 2 from here, and then only 1 from here. So when we do electron transition metals, we always remove from the 4s first if there are any electrons in there. So let's have a look. There it goes, and there it goes onto 3d5. Now if we look at obviously the numbers, and we add all the numbers up, then they should give 23, because iron is 26, obviously minus the 3, and that gives 23. Now, what we do is we lose from the 4s, then from the 3d, so we lose it from there, and obviously that is the new configuration for iron. So as long as you remove from the 4s first, that's the main thing. Okay, let's have a look at some electron blocks as well, just the final thing. So the group number relates to the number of electrons in the outer shell. So for example, group 2 elements have 2 electrons in the outer shell, group 1 have group 1 electron in the outer shell, etc. So that's pretty important. The ones on the left here that are highlighted in red, These are known as S block elements. Basically, the outermost electron sits in the s orbital. That's why we call them S block. This group here in green are known as P block elements because the outermost electrons sit in the p orbital. The purple block in the middle here, these are known as D block elements. And the light blue box here are known as F block elements at the bottom there. So you might not even have that, you might not even use any of them ones, but as long as you know that they are F block. Okay, and that's it. That's basically just a quick overview of atomic structure for OCR-B salters. Please subscribe to the channel. Your support is much, much appreciated. It's free to subscribe. All these are free. If you just click on the little subscription button, the circle in the middle, and you can subscribe to the channel and see loads more videos to do with A-level chemistry. Also, just a reminder that these slides here, if you like the look of them, and you'd like your own copy, then you're free to purchase them. Just click on the link in the description box there. They're really good value for money. All right, that's it now. Bye bye.